Eagles feel familiar in a very specific way. They glide high above the ground, wings stretched wide, barely moving as air currents carry them forward. Watching one fly feels calm and controlled, almost slow, despite the power we associate with them. Interestingly, this is how engineered speed often appears as well. Modern missiles are designed to move cleanly and efficiently through the air, following stable paths instead of chaotic ones. At extreme levels, velocity stops looking violent and starts looking quiet. So here is the question that changes how we see both. What happens when the controlled flight of an eagle meets the speed of a missile? What if eagles were as fast as missiles? Before thinking about consequences, the question itself needs tightening. An eagle is, biologically speaking, a predator built for soaring, scanning, and short, controlled dives. Its body works with air rather than pushing aggressively through it. Speed exists, but only in brief moments. Missile-level speed changes the scale entirely. At several times the speed of sound, movement becomes compressed. Air resistance and heat stop being side effects and start becoming defining forces. So the question shifts almost immediately. Would an eagle still be flying, or would it be moving in short, direct bursts? Could its senses keep up with its own velocity? And how would humans relate to an animal that could cross vast areas before anyone realizes it moved? At that point, this is no longer about power or spectacle. It becomes a question of biological limits meeting an environment they were never meant to handle. To see where those limits might appear, we need just enough science to frame what an eagle can and cannot do. Using a golden eagle as a reference, an adult typically weighs between 3 and 6 kilograms, with a wingspan that can exceed 2.2 meters. In normal flight, a golden eagle cruises at around 45 to 55 kilometers per hour, relying on thermal currents to stay airborne with minimal energy cost. Speed appears only in short, specialized moments. During a hunting dive, a golden eagle can reach speeds between 240 and 320 kilometers per hour, placing it among the fastest animals on Earth in brief bursts. Even then, this speed is not sustained. It lasts only seconds and occurs along a controlled downward trajectory where gravity does much of the work. Flight at these velocities still depends on air behaving predictably. Below roughly 300 kilometers per hour, airflow over feathers remains mostly stable. Feathers flex, redirect pressure, and absorb small disturbances, allowing the bird to maintain control even during aggressive maneuvers. This aerodynamic window is narrow, but it is where eagle flight functions reliably. Missile-level speed pushes far beyond that window. As velocity increases, air resistance grows exponentially rather than gradually. Approaching Mach 0.8, or roughly 980 kilometers per hour, air begins to compress in front of moving objects. Compression produces heat and turbulence, conditions birds never encounter. At that point, feathers would no longer guide airflow. They would vibrate violently, lose alignment, or tear away entirely. Structural forces escalate just as quickly. During a steep dive, an eagle already experiences several times its body weight in acceleration. At supersonic speeds, even a minor directional change would generate forces far beyond what lightweight avian bones and muscles can withstand. Hollow bones reduce mass and improve lift, but they also limit resistance to sudden stress. Perception introduces the final constraint. Eagles possess exceptional vision, capable of detecting prey from kilometers away, but neural signals travel at finite speeds. At missile-level velocity, the environment would change faster than the brain could meaningfully process. Flight would cease to be a continuous series of adjustments and become dominated by momentum alone. From a biological standpoint, the conclusion becomes unavoidable. The problem is not that eagles lack speed. The problem is that every system enabling their fastest movements only works inside a very narrow physical range. The most immediate question would be whether such eagles could be kept or controlled in any meaningful way. On paper, the idea sounds tempting. A creature capable of crossing hundreds of kilometers in minutes feels like the ultimate symbol of efficiency. But control depends on predictability. At that speed, even normal behavior becomes difficult to track. A routine relocation could turn into an unplanned border crossing. Containment would no longer be about cages or habitats, but about airspace, timing, and constant monitoring. The animal would still behave according to instinct, but its actions would unfold faster than human response systems are designed to handle. Another question naturally follows. Could such speed be useful for transportation or delivery? The logic seems straightforward. If nature can do it, why not integrate it? Yet transportation relies on repeatability and safety margins. Missiles succeed at speed because they follow predefined paths with minimal deviation. An eagle, even with extreme velocity, still reacts to wind, visual cues, and internal states. Fatigue, stress, or distraction would introduce unpredictability. What looks efficient in theory becomes fragile once biology re-enters the equation. Some would inevitably ask whether this ability could be exploited for surveillance or military purposes. The appeal is obvious. A fast-moving, self-powered organism that requires no fuel and leaves minimal infrastructure behind sounds ideal. However, military systems depend on reliability under stress. An animal cannot be rebooted, recalibrated, or patched. Its priorities remain biological: food, territory, avoidance of harm. At missile-level speed, a moment of confusion or panic would not be a minor error. It would be an irreversible event. There would also be commercial and entertainment-driven curiosity. Extreme speed has always attracted spectacle. The idea of observing or showcasing such movement would generate interest, funding, and media attention. But observation requires proximity and timing. At these velocities, the act itself becomes almost invisible. What draws attention at human scales disappears at extreme ones. The experience turns abstract, more like reading data than watching life unfold. Even conservation-minded efforts would face contradictions. Protecting a species depends on understanding its patterns: migration, feeding, breeding. Speed disrupts those patterns by compressing space and time. Traditional conservation zones would lose meaning. Interaction with infrastructure such as aircraft routes and communication systems would become unavoidable. The very trait that makes the eagle extraordinary would make coexistence increasingly complex. Across all these questions, a pattern emerges. Each idea appears workable at first glance. Each one carries a sense of technological optimism. But as soon as biological reality is considered, fatigue, instinct, perception, stress, the simplicity dissolves. Speed magnifies small uncertainties into major limitations. What humans would discover is not a super animal ready for integration, but a living system pushed into a range where control, usefulness, and coexistence all become conditional. Turning that speed into something constant would not make the eagle more free. It would make its world smaller, more rigid, and harder to navigate. What feels like an upgrade from a human perspective often becomes a restriction when applied to a living system. So maybe the question was never about how fast an eagle could be. It was about how much speed a biological life form can carry before it stops being an advantage. And if that boundary exists for eagles, it likely exists for many other animals as well. Which raises another question worth exploring. What if a different species pushed its limits in a different direction?